Assalamu alaikum and a very wonderful welcome to everyone. Here is another session on geotechnical engineering, and we'll be looking in chapter number 6 on site investigation, which will be focusing on part number 2, which is starting from F5 to F10. Now let's look at standard penetration test. Now the thing that we stopped last time is this picture over here. Now to understand a basic concept on how to get the soil beneath the ground is to actually penetrate into the soil. So this is one of the simplest method called Macintosh probe, or some other term as JKR probe. Okay, and you're gonna have, this is the hammer that he's holding, and this is the rod, and this is the cone, the penetration pin down over here. So you have three items over here: the hammer, the rod, and the pin. So basically you're gonna hammer this rod down, and then the pin is gonna penetrate into the soil. And so the number of blows it penetrates correspond to the stiffness of soil which is underneath the ground. Okay, so the more the blows means the harder the soil, the lesser the blow means the soil is of soft layer. So that's the most basic concept. Now let's go into a more the more significant technique. Okay, so this is a basic. Okay, we're going to look at standard penetration test. Okay, penetration, you understand, is going to penetrate into the soil, and it's going to again take number of blows, and the number of blows will correspond to the stiffness of the soil. Okay, so this SPT is widely used in United States. Okay, you can refer more of this procedure or details in the standard here. It's a manual in ASTM D1586. It's relatively simple and inexpensive to perform. It is useful in determining certain properties of soil, particularly of cohesionless soils for which undisturbed samples are not easily obtained. Alright. Now the concept is that when you take a soil out of ground, okay, it's gonna be a disturbed soil. So when we bring the sample out into the lab, so it's going to be a disturbed sample. Okay, so it does not actually represent 100% of the soil when it's inside the original location. Okay, so we try as best as possible to be as close as possible to make this undisturbed by taking this carefully outside and preserve it, and to test it in the lab to actually represent the soil at site. Okay, it will never be 100%, so just bear in mind whatever reading that you have from laboratory will not be 100% that correspond to the site, because it's been taken out and it's a disturbed sample. Okay, this is how it is done in a schematic diagram. Okay, so you have your SPT, which consists of a hammer. So this is your hammer, okay, and this is the rod, and third aspect is the split barrel. So this is where the sample will be taken. Okay, so if you cut this, it will be something like this. Okay, so it is called split, means divide into two. Barrel means accommodate for your soil. So when the load is being hammered, okay, so this one will penetrate into the soil, and the sample will be taken inside this barrel. Okay, so this is the first increment, second increment, and it fills up this barrel over here. Okay, so very easy on the schematic diagram side. So the SPT utilizes a split spoon sampler. So this is a split spoon sampler. Okay, it is a 51 millimeter outer diameter, OD is outer diameter, and 35 mm inner diameter tube. So these are the specification for the sampler. Now we have various sampler sizes. and we need to undergo correction because we have different types of sampler sizes. Okay, so this is the split spoon sampler for SPT. So this is one of the size that we have. So it has those the material that is used to construct this sampler and the dimension for this. So this is a detailed sketch of this sampler. Okay, now as the sampler is driven the 457 mm into the soil, so this is the total 457 mm into the soil, the number of blows required to penetrate each of 152 mm increment is recorded separately. So in this case, the 457 is divided into 3 parts, so each part will accommodate for 152 mm. Okay, now the standard penetration resistance value is the number of blows required to penetrate the last 305 mm. Okay, I'm going to show you later in how inside the SI. So thus the n value represent the number of blows per 305 mm, not the whole 457. Okay, the number represent the last 305 mm. Okay, the n values. Okay, so after blow counts have been obtained, the split spoon sampler can be removed and opened to obtain a disturbed sample for subsequent examination and testing. Okay, the soil was stuck inside the sampler. You take it out and take it to lab for more testing for the sample. So SPT results are influenced by overburden pressure, okay, effective weight of overlying soil at location where blow counts are made. So that's why you're going to have some correction being made. Now several methods have been proposed to correct N values to reflect the influence of overburden pressure. Okay, 2 methods are presented. Okay, before we move into the method, let me show you how this is calculated. Okay, so you have your SI. So this is the SI case 1 for your assignment number 1. Okay, so you have your first layer as sand. Okay, this is the one. So graphic log. Okay, and then number blows here. Okay, so here, if you add 75 plus 75 plus 75 plus 75, so you'll get approximately a total of 450 mm. Okay, so according to the statement, it is the last 305 that represent the N values. Okay, so if you want to more zoom in, so the last 305 will accommodate for 4 reading here. So 1, 2, 3, 4. Okay, so the total of this will be 300. Okay, total of these 4 parts is 300. The overall total is 500. So according to this statement, so this is another type of SPT. So this is 457. Here we have 500, and the last number is 305, and the last of this number is 300. So we just take account into this value here. So 24 plus 20 plus 6 will summation into 50 blows. Okay, so this is how we count the last 300 mm. Okay, we don't count this part over here. So we count the last 4 parts here. So same goes with the layer number 2. We have 7 plus 6, 13 plus 7, 20 plus 14, 34. That's how we get 34, and so on of the remaining layers as well. So that's how we calculate the N blow counts. Now let's see 2 methods of correction here. So the first method is established by Peck and the gang in 1974. Now it utilized the following equation to evaluate the Cn, a correction factor to be applied to the N value determined in the field. So if you look at F1, okay, so it relate the correction factor with some values and also the effective overburden pressure. Okay, now this equation are not valid if, okay, the overburden pressure, effective overburden pressure, is less than 24 kN per meter square. So please take note of this. Okay, now we have figure F11 gives a graphic relationship based in part on equation for determining a correction factor to be applied to the N value recorded in the field. Okay, so this is the established figure that you can use So if the effective overburden pressure is greater than or equal to 24 kilonewton per meter square, the correction factor may be determined using either equation F1 or figure F11. Okay, and if the effective overburden is less, the correction should be taken from the figure. So this is the terms and condition if you have the effective overburden pressure over 24 or lesser than 24 kilonewton per meter square. Okay, so this is the figure here. So this chart shows the correction of N values in sand for influence of overburden pressure. Okay, so you have effective vertical overburden pressure, and you have your correspond of correction factor Cn equals to the N after correction and also the N at fill. So this is how you get correction factor, and then you correlate with the effective vertical overburden pressure. Okay. Now, a second method for correcting N values to reflect the influence of overburden pressure. Now, this is by the later researcher, which is Terzaghi in 1996 and Liao and Whitman in 1986. So they utilize this following equation. So this is equation F2, where N stands for the corrected N values after correction. The N prime is N value determined in the field, so the raw NSPT, and this one is the effective overburden pressure. Alright, now this method gives comparable result. It should be noted that the first method, which is equation F1 and F2, result in no adjustment of the N value at the depth where the effective overburden pressure is 96 kilonewton per meter square. So you can replace this and check. Now the second method, which is equation F2, yields no adjustment at the depth where the effective overburden pressure is 100 kilonewton per mm square. So you place 100, so there's no adjustment on the depth. So in addition to the effect of overburden pressure, NSPT results are influenced by, so this is what it influences, the drill rod length. So we have different length of rod. Number 2, whether or not liners are present in the sampler, so whether a liners is present or not. And thirdly is the borehole diameter. So it has a various sizes. Okay. Now table F2 gives some correction that can be applied to measure N values to adjust for these three influences. Through empirical testing, correlation between SPT N values and several soil parameters has been established. They are particularly useful for cohesionless soils but are less reliable for cohesive soils. Okay, so table F3 gives correlations of the relative density of sand with SPTN values. Okay, let's look at this table F2. So this is approximate correction to measured N value. So we have influence from the rod length. So we have variety of rod length. So if rod length is more than 10 meter, the factor correction is 1. Okay, if it's 6 to 10 meter, it's 0.95 and so on. So this is the influence by the rod length that we have to accommodate inside the correction of your raw NSPT. And we also have a standard sampler. So if you have a standard sampler, the factor is just 1. We have another type of sampler. You need to find another established chart for this one. Now US sampler without liners, so the factor is 1.2. Okay, we have another chart. You have to find a full chart of this. This is just a summarization and only certain information is taken here. And for borehole diameter influence, if you have a range of diameter within this range, so the factor is correspond accordingly. So from 65 to 105 15 mm borehole, it needs only one correction factor and so on. Okay, so this table is very useful when you want to find the corrected N values factor. So let's look at the next table, which is table F3. So this is a table showing relative density of sands according to the result of SPT. So please be note that is for sand. So if you get an SPTN value of 0 to 4, which is of sand type, the relative density is of very loose. And so on for the 410, 1030 and 3050 and so on. So it will correspond to the relative density. And you know that if NSPT is in higher value of 50, it will correspond to a very dense condition. okay, of relative density. Okay, here is another table of correlation in SPT. So this is F4. So this is relation of consistency of clay. So previously was sand. So this is on clay. So this one is corresponding between two parameters, which is NSPT N value and also the unconfined compressive strength QU. So this is very useful when it comes to classifying clay. So you have the consistency of SPT, the number is given here, and it will correspond to the stiffness, very soft to hard. Okay, so again, it's the same concept. If we have a higher NSPTN value, we'll have a harder consistency, and it also relates to the unconfined compressive strength. If you have a hard layer, of course you're going to have a higher compressive strength, which is more than 400. Again, you need to refer to this when doing your assignment. Okay, the next established charge is on figure F12. Okay, so this figure shows the curve relationship between bearing capacity factors. So this on the y-axis, and the x-axis shows the type of soil that we're going to have, from very loose, medium, and very dense, and it also corresponds to the NSPT value from 0 up to 60. So all of this established figure is important in making a decision in geotechnical interpretation. Okay, so this is a zoom of the previous figure. Okay, you can see more clearly. Okay, and this is the photograph of the SPT at site. Okay, you can see a big machine here, and also some personnel conducting the SPT inside this ground. Okay, so this is the mechanical SPT. We have also the manual NSPT. Okay, so you can look up for that inside any of the textbook or the videos. Okay, so next we're going to move on to subtopic F6, which will be into another type of testing, which is the cone penetration testing. Okay, so as you have been briefed, SPT is commonly widely used in United States. For CPT is widely used in Europe, and however in recent times is gaining favor in the United States. Okay, so you have to know what's the advantage of using CPT. Okay, for CPT, you're going to be referring to ASTM D3441 and also D5778 for more details and complete procedure. Okay, now one of the main advantage is that it has the advantage of accomplishing subsurface exploration rapidly without taking soil samples. Okay, if you compare with SPT, you need to take samples out of the soil, but for CPT tests, the soil remains. You're just going to take the values out. So we're going to see more details in the later discussion. Okay. Okay, the next will show you on the schematic diagram of CPT, which consists of a vehicle. Okay, in this vehicle, it accommodates for a computerized measurement system. Okay, and also this moving rod down here. Okay, so as it moves down, all of the reading will be taken into this computerized system inside. Okay, so it's the same concept where it penetrates into the soil, but it doesn't take samples out. So it has a continuous procedure, and as it continues to penetrate, all of the parameters will be extracted. Now, what are the parameters that we can have from CPT? So these are the step-by-step process, and the sizing and so on. It's similar to SPT, the concept of sizing and everything, but it's just not taking sample out of the ground. So the main important is that you're gonna have this type of information, which is cone resistance, friction resistance, and also the friction ratio. All of this will accommodate to the stiffness of soil later on. Okay, so this is the raw data taken from CPT. Okay, And this is figure F19, which shows soil classification based on Bigman cone penetrometer test. Okay, so from here you get data from site, which is friction ratio, okay, and also the cone resistance, as I have presented earlier, and then we can just choose what type of soil it is based on this two data over here. Okay, and here's is another established information. So this is a simplified soil classification chart for standard electric friction cone. Okay, again we have to take this from CPT, okay, the cone resistance and also friction ratio, and from here it'll tell us what type of soil it is. Okay, and this is the lorry I was talking about, which accommodates for the CPT testing. Okay, so this is the one that's going deep into the soil, and if you open this lorry, you're gonna see a systematic arrangement of a computerized system, which will record all the information taken from this drill. So there's a lot of sensors and cables inside this lorry. Okay. All right. Next, we're going to move on to another type of testing. This is a much more simple and small in size, which is on vane test. Now, what's the importance of this test is that now this test is used to determine in place shear strength. So please note, whenever it refers to vane test, it refers to shear strength. For soft clay soils, particularly those clay soils that lose part of their strength when disturbed. Okay, so whenever you have vane test, you know that you're going to take a measurement of the shear strength. So let's see the basic concept. This is the vane test equipment. So you know that you're going back to mechanics of materials, where you apply a torsion movement and you'll be able to know what's the strength. So it's a similar concept with this one also. You apply torsion effect, and then the resistance will accommodate for the shear strength of the clay sample. So this is a formulation which has been established by Scampton and Bishop in 1950. So we have the relationship between cohesion of the clay, the torque, the diameter of the vane test, and also the height of the vane test. Okay, F3 is a straightforward relationship. Okay, and they also have some established chart that you need to apply, because you need to apply some correction. So this is the correction vector for vane shear test. You have to take the sample for laboratory testing, and you find the plasticity index using the method that you used earlier, and you then correspond to the correction factor, which is denoted by mu. Okay, that was on vane test. So we've looked into three types of testing. The first was on standard penetration test, and then we follow by the cone penetration test, and lastly was on vane shear test. Okay, now we're going to move on to a much more sophisticated soil exploration method, which uses two main sources, which is the first one is from waves, and the second one is from electric current. So these two sources can also determine what type of soil you have at site. Okay, this is more sophisticated one. Okay, so we're gonna look at geophysical method of soil exploration. Okay, so borings and test pits are both time consuming and expensive, because we gotta dig soil out, and this will accommodate with lots of instrumentation and also big machines. So that's why it's time consuming and expensive. Okay, so moreover, they give subsurface condition only at boring or test pit location, so it's pretty limited. So if you take a borehole at a certain location, so whatever result you take is just for that borehole. So of course, if you have more boreholes, you're gonna have more information, but if you have just one, you might want to have some interpretation of the other location which is related in the same or near the borehole area. Okay, so you're gonna have a lot of assumption if you only have one borehole. So for geophysical method, it is more quick and less expensive, and it can cover greater areas more thoroughly. Okay, because it's just by the use of wave, and it can accommodate for a larger area. Okay, so two particular geophysical method, which is first seismic refraction, which uses waves as a source, and another one is electrical resistivity, which uses current from electrical sources. Okay, so when you use this type of geophysical testing, you're gonna have two type of instrumentation. One is the one that generate the source, okay, and another equipment is for the detection of the source. Okay, from that we're gonna have the value, and then we're gonna correspond to what type of soil it's gonna be. Okay, so for seismic refraction method, okay, you're gonna have this type of equipment. So this is the seismograph, the detectors, and the source. So you're gonna basically explode one area here, and then by the explosion the wave is generated, and then it's being detected by these sensors, and then it'll be read through this seismograph over here. So you're gonna have a value for this, which correspond to the wave movement. Okay, so that's why we say that it covers a greater area without taking samples out. So this is how it is conducted, and in the end we're likely to have this type of established information. Okay, for a property of wave, let's say below 3000 feet per second, this is the value of the wave. It corresponds to this type of soil. So this is the wave value, and this is the correspond to what type of material it is. So if the velocity is for example within 3000 to 5000 feet per second, so this one will correlate to a coal type of material. So again, same goes for other velocity values. It corresponds to the type of material that we have. So we have different type of materials such as shale, soft, hard, and so on. Even for pure ice, we will have a value for the velocity. And if you want to have a more nice way of presentation of the information, you can have something like this. So this is the depth, and this is the values. So the values is correspond to this contour color over here. Okay, so of course the red indicates it is of hard soil, and the blue indicate it is of soft soil. Okay, so this is what you represent to the client when it comes to your result of geophysical testing by seismic refraction test. Okay, so here's another type of testing of geophysical, which is electrical resistivity method. The same concept, it just uses a different type of sources, which is the current sources. So the unit is in ohm dot centimeter. So for a value of your measurement here, you correspond to the type of material, and you see that the type of material is of this type of classification. We have wet to moist clay soil, wet to moist silty clay. So this is of assumption, and it's not really accurate, because it's like it's either wet to moist, so it has a range. Okay, so it needs a more interpretation of this. Okay, so this is a basic schematic diagram if how the electric source and the detector is being distributed inside this test, electrical resistivity test. Okay, simple formulation that connects all of these parameters. Okay, and the most important thing is that you have an established chart. Okay, again, same with the previous concept, and also the end result will likely to be of this. Okay, so from here the contour tells us that the red color is of a hard layer, and the blue layer is of a soft layer. Okay, right, so when you have all this type of testing and result, you need to arrange it in such a way that it's representable and easy to understand. So this will be discussed in the next chapter, which is in records of soil exploration. Again, I have given you a lot of SI example in your assignment and also in your class in integrated design project. Okay, so you just need to arrange in such a way it's nice to look at. So all the basic information are recorded here. Who's recording, the location, the time, and so on, and the detail of the testing is recorded here. Okay, nothing changes, it's the same. You have a number of SPT and also the corresponding type of material. Okay, so for different region they will have a different type of formatting, but all the information, the basic information will be written here. Okay, we have one, basic information, second, the depth, and third is the type of material. Okay, so you can make a comparative study between an SI from India with a SI from America and also from the European countries. Okay, it's gonna be the same. Okay, and another type of presentation is something like in figure F30, which is geologic profile sample. So if you want to have interpretation from this boring log sheet in a form of graphical presentation, you can have it something like this. Okay, so this is a more to like a layman type of presentation where everyone understands this, especially a client without technical background. You know that the layer here is of hard layer and the top layer is of soft layer. So it's actually presentable to every single people which is of technical or without technical background. Okay, now let's look at the last conclusion. So analysis of soil and design of associated structures are of questionable value if the soil exploration data are not accurately determined and reported by the geotechnical engineer. That's why every single development starts with you as a geotechnical engineer. Okay, you need to provide accurate data in order to move on to the development of structure. Okay, if you're unable to provide this, then you're gonna have the problem later, because it's a chain process. Okay, you're starting geotechnical from the ground and then you're gonna change it to chain. Okay, it's a chain thing. You're gonna relate it to the structure and then to the people. Okay, if you provide a wrong data, geotechnical, it will affect the structure, and later on you're gonna affect the tenants or the people living in the structure as well. So it's a chain type of relationship. Okay, so it's very important for a geotechnical engineer to provide accurate result. So learning to conduct soil exploration well requires much practice. So the more you are at site means the more best you are in terms of geotechnical interpretation, and varied experience under the guidance of experienced practitioners. Of course, from a junior perspective, you need to learn from your seniors. Okay, not only it is a complex science, it is difficult art. Okay, so that's all about it for this chapter 6. Okay, so I'm gonna see you in the last chapter on chapter 7. Okay, so for the time being, stay safe and I'll see you again. Thank you very much.